Alright, in this video I'll be talking about another example for shooting method where we want to solve a differential equations with two sets of boundary conditions, one on the one at the x equals 0 and the other set is at x equals L. So that's the one-dimensional problem, but it involves with 6 coupled differential equations. So basically there's an electrode where there's a liquid coming from left to right, and then we have concentration of species in the fluid. The concentration of species changes over time and in space as the fluid goes from left to right over the electrode. An electrode is placed horizontally, so the equations that we get by looking at this problem would look something like this, where Im is the current in the electrode or in the matrix, Is is the electron in the solution, phi m and phi s are the potential in the matrix or electrode and in the solution, C is the concentration of the species that we want to absorb by the surface, and then W is the first derivative of the concentration. So this second order differential equation for this whole problem turned out to be a first order system of nonlinear of differential equations, where we have these 4 parameters, basically these 5 parameters, 2 are currents, 2 are potential, and 1 is concentration, and the last one is the derivative of the concentration. So derivative of this vector is equal to these sets of equations where A and S, beta, these are parameters or the constants of the problem, as well as G and H and M and A. So all of these parameters are explained in the problem statement. I'm not going to go over them in this video, but just to let you know that these are constant, and our unknowns basically are these 6 variables. So the boundary conditions are given. Few maybe on current and potential on one side, and others are on other currents and potential on the other side. So we convert the problem into our generic form of first order differential equations, like dy dx equals some function of y, where this y is our unknown vector. If you want to use RK4 to solve this problem, then as long as our problem is written in the generic form, then RK4 is written like we have 4 k's if you remember, and each k is related to del x, or the interval along the x-axis times the function evaluated at certain points. And so we can easily write these in a MATLAB script to calculate the progression of 6 variables that we have here at every delta x, or at every x from 0 to L. So now I'm going to skip over the rest of the details and just jump into the MATLAB script. So in MATLAB script, if we want to solve this problem using shooting method, then we have to create some error function, because so when we talk about shooting method, we always try to make an error equal to 0 by tuning a parameter which is our shooting parameter. Now in this case, we have to come up with some error function which is involved with some tuning parameters to be able to solve problem as an initial value problem. Okay, so then the way we approach this is we have to convert those boundary conditions that are given at x equals L to something which are not given to us at x equals 0. And then by solving the problem using RK4, we tune those parameters that we guessed at x equals 0 to make the error on the values or the boundary values that are given on x equal L. So we have to create an error function, which basically gives us how much error we are making on the guess of the values at x equals 0 to make those boundary values at x equal L. Alright, so here is a MATLAB script to solve that problem using shooting method. I have some global variables by using a global syntax in MATLAB, which makes every variable along this list as a global variable. That means we can use these variables in any function without having these variables passed through the argument list of any function. All right, so these are input parameters or problem constants that are given to us from the problem statement. Then I create these 6 variables exactly as I had in this document. I have 2 currents, 2 potential, 1 concentration, and 1 derivative of the concentration. So I have the same thing here, where this is the derivative of the concentration at x equal L. Then this is the concentration at x equals 0. This is phi m at x equals 0, phi s at x equal L, and then current Im at x equal L, and current in the solution at x equals 0. I only have some comments here. So these are the boundary conditions that are given to us. You see that some of them are at x equal L, like this, and this, and this. So 3 of them are at x equals 0, at x equal L, and then the other 3 are at x equals 0. So you see that it's completely split boundary conditions, and we need to use shooting method to solve this and convert it to initial value problem. Right, so we split our x, we find our dx as the difference between 2 successive x points. We have to make an initial guess. So the values that I picked are the matrix current at x equals 0, then potential in the solution at x equals 0, and the slope at x equals 0. So these are what I'm guessing. So these are not given to me. If you compare this list with these 3, you see that these 3 that I'm guessing are not actually among this list. So I'm guessing these that are not given at x equals 0 by making those 3 that are given to me at x equal L, which means I'm gonna find the error. I'm gonna find the error for phi s at x equal L, Im at x equal L, and dc dx at equal L. I'm gonna find the error that I make for these 3 variables by changing these 3 variables. Okay, so the current in the matrix, the potential in the solution, and the slope or the concentration or flux of the concentration at x equals 0. So anyways, I'm going to call this error function, and if you go to this error function needs the unknown vector. So with this, this error function requires the guesses that we make. So we come in with these 3 guesses, then we put the other 3 values that are given to us, which means the current in the solution at equals 0, current in the potential in the matrix at equals 0, and the current at x equal, the current in the solution at equals 0, the potential in the matrix at equals 0, and the concentration equal 1 at x equals 0. So these are given to me. The other 3 I'm guessing, so now I'm going to have 6 values all given or are available to us at x equals 0. So we're going to start with this y0. I'm going to call an RK4 function, which I grabbed from before, and then I solve the problem from 0 to L. At the end of the solution, at x equal L, I'm going to backtrack and extract the slope at x equal L, potential in the solution at x equal L, and the current at x equal L. These are the current in the matrix. So these are the boundary conditions that I know from before, but I'm also solving the problem. So I am having these using my solution, the difference between these and what I'm given at x equal L would be the error that I'm making. So this y out, which has 3 elements in it, would give us the error for every 3 elements here. So then by making y out 0, I'm going to tune these 3 guesses to find the least error I make. I quickly go over RK4. So RK4, you have to calculate 4 Ks using the function evaluation and then get the average over these 4 values. The function I'm using is basically what I exactly have in this document. So the function would be the right side of this, which means f of y, and I'm just rewriting those 6 lines into my f of y. So ai minus s times im is exactly these values. I think this minus is the typo, it has to be plus. Anyway, so right, so now I have my f of y. I go back to RK4, so RK4 is done by having function, and then this RK4 spits back the result, the full solution from 0 to L to this error function. And then error function only requires the last 3 values to subtract from the boundary conditions for the current, potential, and the slope. I find 3 equations that I have to make 0, and in the main code, by solving fsolve, I'm going to find the root of this error L, which is the guess values that I started with. And then by having the solution to this root finding problem, then I'm going to have my correct guesses. So now my guesses are found by this point. Then I put these 3 back into the into another matrix or another vector with the other boundary conditions at x equal L. So basically my boundary conditions at x equal L are completely correct because those 3 that were guessed now corrected using this fsolve. So then I call my forward the RK4 one more time to basically solve the problem with the correct guesses, and then I get all the solution. I split them into 6 variables, 2 currents, 2 potential, the concentration, and the slope. Then with the definition of the problem statement, we also calculate the over potential, which is called eta, the difference between the matrix potential, solution potential, and some constant E naught. So I put all I split the solution into these 6 variables, and then I can go and plot everything I want. Like in panel 1, I'm plotting the concentration. In panel 2, I'm plotting the matrix potential and solution potential, as well as eta, which is calculated here. In panel 3, I'm plotting the current, the matrix current, and solution current, and that's it. So if I run the code, you should get, so now you see that the fsolve is iterating until it converges. So you see that the solution found, and this is the error that is made. That means the error is very small. That means now the guesses are fine. With those fine guess points or guess values, then you can go and resolve the problem. And so this is the solution you get. So this is the concentration. Remember we have 2 potentials. The phi s is red and phi m is blue, and then 2 currents. The I sub s and I sub m. So I hope this helps you, to better understand how shooting method for a problem with multi-dimensional or multi variables. So, all right. So thank you so much for watching.